So today we will go to the mixture design lecture. Okay, the mixture design actually is used for the formulation work. If the process is a mixture such as drug formulation, chemical compositions, then you can use mixture design. This design actually produce runs to model the response in terms of relative proportions of the components. So when one component increase, the rest of the components proportion will actually decrease. For example, component A increase to 70%, then component B will decrease to 30%. So the sum of the component proportion is always 1 or 100%. In the mixture experiments, the factors are the components or the ingredient of a mixtures, and their levels are not independent. So from here you can actually see three design where P equal to two components will be the first design. If you have three components, then you will have B and C designs. Okay, what is the difference between B and C? It will be the proportions. Let's B have less proportion and C has more proportion. Okay, in the simplex design, uh, in mixture experiment, actually there are many designs, and simplex lattice design is the one that commonly used if you have a very simple formulation. Okay, simplex design are used to study the effect of mixture components on the response variables. Okay, a P and M simplex lattice designs for P components consist of points defined by the following coordinate settings. The proportion assumed by each component take the n plus 1 equally spaced from 0 to 1. It means that uh, if you have n equal to 2, then the proportion will be 3. Example, P equal to 3 and n equal to 2, then your proportion will be 0 divide with m, 1 divide with m, 2 divide with m until you get the final is 1. So in this case, m equal to 2. So you have proportion which is 0, 1 divide with 2 as your m is 2. So 2 divide to 2. So you will get 1. From here, you will have 3 proportions. 1, 2, 3, which is m plus 1 equal to 2 plus 1, which then you will get 3 proportion. Okay. So it will actually have 6 here, 6 experiment runs with these combinations, and this combination actually consists of pure brand and binary brand. Okay, pure brand is 1 and 0, binary brands is 0.5, half, and 0.5 and 0. Okay, this is how the simplex design for P equal to 3 and M equal to 2, how it looks like. So from here, you will have 0.5 at here and 0, and the pure brand is 1. So if you go to the design, you can actually pick the same compositions where the mixture components, which is the P equal to 3, okay, and then you have total which is 1 or 100%. Then from here, once you choose the three components A, B, C, you can actually name it, for example, alcohol, water, oil, anything based on your formulation. So when you click next, you will come to the simplex lattice design. Augment design and the replicates you select to 0. Okay. Then the order quadratic equivalence to it means quadratic, it means the n equal to 2. Okay. From here, quadratic, the order is power 2. It means n equal to 2. So you will have 6 runs like previously I mentioned. So when you click next, you will go to response, and then click another next, you will come to this page. And then there are 6 runs from here, which with the combination of the pure blend and binary blend. So you have 3 components and your n equal to 2. So go with another example. P equal to 3 and n equal to 3. By manual calculation, your proportion you will have 0, 1/3, 2/3, and 1. So you have 4 proportion, which is n equal to 3 plus 1. So you have 4 proportion. And you will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A total 10 runs. This is the design when you have 4 proportions. Okay, come to the design aspect. The component you will select 3 as well because P equal to 3. So the difference will be the order. Okay, just now is the quadratic, which is n equal to 2. Cubic will be n equal to 3 because it is power 3. So you untick the augment design and reduce the number of runs to replicate to 0. Then you will have 10 runs, which similar to the one that we count just now. So you have 4 proportion, which is 0, 0.323, 0.67, and 1. So this will be the experiment runs and the combinations that if you choose P equal to 3 and N equal to 3. So for a case study, if you want to formulate a hand sanitizer as an example, okay, and you choose P equal to 3, and we choose the proportion, okay, the n equal to 3, so that we have 4 proportion in here. So from here, the mixture component is 3, and I key in the ethanol hydrogen peroxide glycerin as the main component in the hand sanitizer. So we use the coded value, which is 0 and 1, and the total will be 1 for the overall formulation, which is 100%. So next, we choose the cubic so that the n equal to 3 and the proportion will be 4, which n plus 1 equal to 4. So you will have 10 runs, and then the response is antibacterial activities in percentage, let's say. which which proportion or which combination or which formulation can give the highest antibacterial activity. So after you formulate this, then you will run the experiments. And after you run the experiments, then you can go to the analysis and optimizations like what I already taught in three-level factorial and the CCD. Okay. So this is another case study formulating a detergent. This will be a more complicated example where you have total 9 and your formulations cannot exceed 9. Okay. And the order is quadratic. It means the m equal to 2. So your p is 3 and m is 2. And it involves the augment design here and triplicates. So these is some uh, the examples. The formulation will not exceed 9%. Okay, because we just now already set 9. So anyhow, when you adding water, alcohol, and urea, it won't exceed 9%. Okay, and then you run the experiments, you get all the values, then you can actually look at the summary, the constraints in the design, and you can actually go for the ANOVA, and it will show you the model is significant or not, and lack of fit is significant or not. Okay, so because you have two response, hence you will have two equations. One is the viscosity and another one will be the turbidity. From here, the model graph, it will show you this triangle shape design as what I shown you in the previous slides. So from here, in the optimizations uh, column, they will, if you minimize, we will, okay, in here we will minimize the viscosity and turbidity, okay, like in the optimizations lectures that I've given, okay, then they will predict the solutions for you. 5% of water, 2% of alcohol, and 2% of urea will give you the lowest viscosity and turbidity. And this is how it actually looks like if you go to the model graph. So this is the end of the mixture design lectures. If you have any questions, you can actually type me or I will open a forums or a chat in e-learning. Then you can ask questions there. So before I end my lectures, I just go a summary what you have learned actually along my lectures. You have actually learned the design of experiments, three-level factorials, and screening using the two-level factorials, characterizations, two-level factorials, then method of steepest actions for the improvement of the range to find the optimum region. Then next is the optimizations, which you will find the optimum point using CCD. Okay. Finally, you go to confirmations or validation. Then lastly is the mixture design. Okay. If you have you want to have more readings, you can refer all these reference that I listed out. Okay. There are few reference and or you can go to search in Google if you need more information. All right. Okay. Thank you, class.